GPU. General Purpose Computation on Graphic Processing Unit, GPU, exploit GPU's massively parallel computing architecture as accelerators in highly performance or embedded systems. This is a response to the power wall issue. So what we want to achieve here is to get more parallelism, to get more performance at a lower energy cost. This is an illustration of this. We are here with the Kepler architecture at NVIDIA, and the next generation should be much more power efficient because we should be able to deliver as a peak performance between 14 and 16 gigaflops per watt. This is extremely high. So GPU is based on the offload model, so you have to do a remote procedure call to launch some computation on the accelerators. In this case, the accelerator is a GPU. And you have to transfer the data in and out to get the computation possible. You have another instantiation, which is the AMD APUs that stand for Accelerator Processor Unit. I'm going to describe briefly these two kinds of architecture. So the architecture is based on stream computing. So the idea behind this is that you have some input vectors with elements, and you do some independent computation to produce another output vector using some kernels or some functions that will be applied to the element of the input vectors. So this way you get a huge number, a massive parallel computation through this organization. Of course, this one is a bit strict. In reality, it doesn't have to be as strict as this one, but this is the form of data parallelism that is aimed by the GPU organization. So it is important to note that there is no data dependencies between the computation on different stream elements. This is an example of such architecture. You should note the big numbers here. That's a Titan machine at Oak Ridge in Tennessee in the USA. 18,000 Tesla GPUs. And the peak performance is 27 petaflops that are provided by the GPU. And the achieved performance is 17.59 petaflops on LINPACK. LINPACK is a program that is solving a linear equation. So the architecture, for instance, just to illustrate some numbers on GPUs, you have 7 billion transistors, 15 Kepler streaming processor, SMX, and this can deliver more than 1 teraflop double precision per board. It's a huge chip. It's GDDR5 and it's connected with the CPU with PCI Express Gen 2 or 3. So the architecture is organized this way. You have an SMX here. This is an SMX. You have some local memories that can be shared between the core of the SMX. And you have the device memories, the global memory of the GPU that is connected to the CPU here through PCI Express. So when you do copy in and copy out between the CPU and the GPU, this is between the CPU memory and this device memory. There is no sharing, so there's this small memory is shared only between the core inside an SMX. And there is no global synchronization possible between the cores of different SMX. So to keep such architecture busy, you need a lot of threads because you need at least one thread per core, and because the device memory is very far from the cores, it is highly pipeline, and so this is hundreds of cycles to access memory. So you need to have thread to keep at least one per core, and also enough thread to pipeline the memory accesses that need to be pipelined, that need to be amortized in terms of penalty, access penalty. So you need thousands, and it's more like tens of thousands of threads to keep the architecture busy. The AMD Fusion APUs for accelerated processor architecture, the idea here is to put in the same processor, same chip, you put the GPU and the CPU. The GPU is usually not the high-end, the latest one. It's something that is a bit smaller, and the CPU it's a multi-core. And you have a unique address space. You have a global address space in here. So the CPU and the GPU can share some data directly without copy in, copy out. So, but there is two kinds of accesses. So there is the non-coherent accesses. That is, for instance, the GPU write directly to the memory, and so in this case, this is invisible from the CPU, and the L2 cache then is not up to date. Or you have the one that takes into account the coherency, but in that case, the L2 cache sees the modification, it is updated, but this is slower. So this path is slower, you have less bandwidth through this path. So you have the choice of choosing slower copies, access to memories, but keeping the things consistent, or you can have some faster access, but in that case, the CPU is not aware of the modification, and vice versa. So the questions for this course: what is the difference you see between a CPU discrete and a discrete GPU and an APU? The difference in here is more in terms of programming. That's on this. And now a question on parallelism. Assume the number of cores of a GPU is 1500, that the load latency is 500 cycles, that the load fetching data from the memory is launched every 10 cycles. So every 10 cycles per thread, a thread launch a read access. No constraint on the memory bandwidth. How many threads do you need to keep the architecture busy? So what is the minimum number of threads with this condition to keep everything at full speed? Some references. There is a lot of information on this site. You get the NVIDIA GTX white paper. This is another paper on the APUs, and this is another presentation on Fusion APUs. See you in class.